Good afternoon. On behalf of Engineers Australia, I'd like to welcome you all to our Thought Leaders series, Economy and Sustainability Driven Designs for Concrete Floors. My name is Amanda and I'll be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them and their cultures and to elders past, present and emerging. Before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, Bentley Systems. Bentley Systems is an infrastructure engineering software company that provides innovative software to advance the world's infrastructure, sustaining the global economy and environment. They are the leading global providers of software solutions to engineers, architects, geospatial professionals, constructors and owner-operators for the design, construction and operation of infrastructure. Today we will hear from 3 speakers, followed by a live audience Q&A, and as always I encourage you to send questions through to our speakers via the chat box. And I'd like to welcome our first speaker, JD Camden. JD is a design engineer at Interspan, where he's responsible for the design and analysis of slabs in low to medium rise buildings, design of RC slabs and post-tensioning slab as per AS 3600, and slabs design using RAM and RAPT. With his background in civil engineering, JD brings a wealth of knowledge to our topic today. Please welcome JD.
Thank you for the introduction, Amanda, and thank you for Engineer Australia for giving us the opportunity to do this discussion on post-tension slab. So firstly, we'll have an introduction of post-tension slab, what they are, how they work, and why we use them. Post-tensioning is a practical way that allows us to use concrete in a more efficient way. Compressive stress is put into the concrete member through the tendon before it begins its working life and is positioned in areas where tensile stress will develop under working loads. As we know, concrete is strong in compression, but rather weak when it comes to resisting tension. The introduction of the pre-compression in those areas that will become subject to tension means that the concrete will behave as if it had tensile strength of its own. A post-tensioning system is an arrangement of tendons and anchorage in the slab that carry out post-tensioning. The 2 main systems that we use are the monostrand system, which is where we apply the hydraulic force to each individual strand and progressively transferring the load to the concrete. It is often referred to as a slab system because it is ideally suited to the full slab of buildings. The other system that we use is the multi-strand system, whereby the load is applied simultaneously to all strands. Multi-strand post-tensioning system is mainly used in large structures, such as bridges and dams. On the screen at the moment, you can see the multiple components we have in the monostrand system. The strand is a cable that we will apply the load to. The duct is a grey flat conduit that will encase the strands. The anchorage on one side, you will have an onion, which will hold the cable into the concrete when the load is applied, and the anchor where the stressing block is applied to apply the stress. The next slide has a short video to show you how the system works together. So the cables installed inside the duct and profile, and we'll have the onion on one side and the anchor on the other side. And after the concrete has been poured, you'll put the jack at the anchor and apply the stress to it, like the video is showing. So why do we use post-tensioning? Post-tensioning has many advantages over conventional RC slab. They provide a larger clear span. That is, they reduce the amount of columns, giving us more space to work with. A post-tension slab will span approximately 25% further compared to a reinforced concrete slab of the same depth. This results in a larger column-free floor areas, which generally greatly increase the flexibility of use for the structure and can result in higher rental returns. We also provide a thinner slab. Compared to an RC of the same span, PT slab will require less depth to achieve the same deflections. By reducing the number of columns and having a thinner slab, this combination provides a lighter structure, reducing the building mass. We can also, post-tension also allow the rejection of cracking. The tensile force in the slab to the post-tensioning cables reduces the risk of cracking of the slab. Cracks can be formed, small cracks, but they are held closely together by the post-tensioning forces. There is also, we can reduce deflection, particularly in long term, by using the post-tensioning forces. We also have a reduced story height. A post-tension slab will be 80% of the depth of a reinforced concrete slab where the spans are the same. The reduced section allows the overall building height to be reduced, or alternatively, additional floors may be added within the original building envelope. Using post-tensioning also allows for faster cycle time. The earlier stripping of the formwork and reduced backpropping requirements enable faster construction cycle and quick to reuse formwork. Once final stress is applied, formwork can be stripped and slab can be poured in 3 or 4 days. Using post-tensioning also greatly reduces conventional slab reinforcement. The reduced material quantities in concrete and reinforcement greatly benefit on-site cranage requirement. The strength of the post-tension is approximately 4 times stronger than conventional reinforcement. The total weight of reinforcement that's bearing this PT slab is reduced by around 50 to 60%. Here at Indispan, we use a combination of design software to design our post-tensioning slab. Our main software is RAM Concept from Bentley. I won't talk a lot about this given we have Carl and Jonathan that will go in depth on the use of RAM following me. Let's talk about a few jobs that we have done and why post-tensioning has been preferred over conventional slab. The Marriott Hotel in Dockland that we recently completed was built partly on top of an existing shopping center. While the construction was underway, the shopping center remained mostly operational. The challenges there was that given the lower slab were already constructed and not the whole of the building was going to be demolished, the location where we could have support were limited, which gave us large spans to work with. One of the biggest span on the transfer deck was 14 meters, something that would not have been able to be achieved at the same depth using conventional deck. Given that there was a building below it, there was also limited amount of backpropping that we could use during construction. And to help on this, the transfer beam were poured in 2 phases. The first pour was used partially to support the second pour using the uplift provided by the PT force. Another project that where PT was instrumental in achieving the requirement was a Corio K approach ramp for the new Spirit of Tasmania terminal in Geelong. The PT beam was used to support both of the ramp and was spanning 25 meters. In this project, we have used multi-strand system. Minimizing deflection was a priority because we had to construct the ramp on top of that beam, and it would have affected the construction of the ramp and its adjoining landing. Next project is a Harrod Road project in the UK. Interspan was asked to review the design of the building because the builders required a faster construction time. In doing so, we also reviewed the slab depth and the columns. On the table below, you can see the comparison of what we were able to achieve using a conventional versus a PT slab. We have saved the amount of concrete. We have reduced by over 100 meter cube, and we have reduced the thickness from 200 to 250. Sorry, the other way, from 250 to 200, and we reduced the number of columns that we use from 83 to 65. The next project that I would like to talk about is the Wardian in Canary Wharf, still in London. We have designed a 200 mil thick slab with local 250 edges versus a concrete RC slab of 275 thick. The reduction in the combined height of the two towers are almost 8 meters, equating to 2 levels. The tight program of 100 weeks was only able to be achieved using PT, where we were able to do 1 pour per tower per week. The total savings was of 7,000 meter cube of concrete and a reduction of 25% in the load at the foundation. We were also able to save reinforcement in the order of 350 tons in slab reinforcement. Lastly, let's talk about safety and environmental outcomes. Quality and certification. Interspan is a member of the PTIA, and as such, we are required to meet specific criteria which identify technical competence, insurance cover, management plans, and resources to ensure the safety and quality of the product and services we provide. Interspan is also working towards obtaining a new certification recently introduced in Australia, which is the CARES certification, which relates to the supply and install of post-tensioning system. Interspan is dedicated into achieving those to ensure the safety around our work, safety of the guys on site, and everyone working in the building industry. The environmental impacts of post-tensioning is quite obvious. By achieving thinner slab, larger spans, and lighter structures, we basically use less material. As we know, concrete industry contributes a lot in CO2. It's around 5 to 6% in the world. And by reducing the amount of material we use, we're having a significant impact on reducing the CO2 and helping us fight a little bit global warming, which is partly of both points. Reduction of the embodied energy of the whole buildings, which is achieved by having less materials, producing less materials that we are providing in the building itself. Thanks.
Thank you, JD, for your presentation. And now I'd like to welcome our next two speakers, Carl Gullaroot and Jonathan Hirsch. Carl started his career as a structural consultant, working on a variety of building structure types before joining the RAM software team in 2008. Carl is currently the project manager for the RAM concept software for Bentley Systems and was previously a technical support engineer for the RAM products. He is a licensed professional engineer in the US. Jonathan is a development manager for Bentley Systems. His experience includes development of the RAM concept product for the past 18 years. Jonathan has 9 years of experience specialising in the design of post-tension concrete structures and pioneered a technology using genetic algorithms to optimise the design of these systems. He is a fellow of the Post-Tension Institute in the US and is a member of its Technical Advisory Board and a chair of BIM subcommittee. Please welcome Carl and Jonathan.
Thank you to everyone joining us today for our presentation titled Economy and Sustainability Driven Designs for Concrete Floors. My name is Carl Gullaroot. I'm a product manager at Bentley Systems, working with the products in the RAM brand. And I'm here with Jonathan Hirsch, the lead developer of RAM Concept. Today, there is increasing pressure on structural engineers who design concrete floor slabs to deliver designs with floor depths reduced as much as possible. Until recently, economic drivers aimed at minimizing construction costs have largely fueled that demand. Today, climate change concerns are forcing structural engineers to consider sustainability goals with their designs and look for ways to limit the use of construction material. For concrete buildings, this has increased the demand for thin post-tension concrete floors with lower reinforcement ratios. And it has also forced engineers to consider other technologies like voided concrete slabs and steel fiber reinforcement. The advantages of thinner concrete floors, which are listed here, are well documented and closely associated with concrete material reductions that I just referred to. Less concrete decreases building mass and weight, which allows for smaller columns and foundations. Thinner slabs also mean less exterior cladding, and that further reduces the amount of construction material needed to build the structure. My personal view is that economic and sustainability pressures will not ease in the near future, and it's likely that the demand for thinner concrete floors will only continue to increase going forward. Sustainability goals have pushed many structural engineers to calculate embodied carbon during the design phase. Those of you who are familiar with embodied carbon calculation have likely seen Sankey diagrams similar to the one shown here. These diagrams help visualize what building components and materials are the biggest contributors to the overall carbon footprint of the building. There are a few takeaways from this diagram that strengthen the connection between overall building sustainability goals and the demand for thinner concrete floors. First, we see that the contribution of the floors is the largest contributor of building components. Second, we see that concrete is the largest contributor of the building materials, and that a significant portion of that concrete is used in the floors. Finally, we note that exterior walls are the second largest contributor of the building materials at nearly 25%. As we just discussed, reducing floor depth reduces the overall building height and at the same time decreases the amount of exterior cladding required. So decreasing floor depth can also decrease embodied carbon in other ways besides the volume of floor material used. All of these points confirm that reducing concrete material and reducing floor depth can be efficient ways to reduce embodied carbon for building structures. Construction costs and sustainability goals are just a few items on the growing list of constraints that a structural engineer must consider during design. With today's aggressive project schedules and budgets, it can be difficult to deliver quality designs that are both economical and sustainable without devoting less attention to other important considerations like coordination tasks or constructability. And the push for thinner concrete floors and slabs increases the risk of issues that can occur. Thin concrete flat slabs, for example, are more susceptible to brittle failure modes like punching shear. They are also more susceptible to excessive cracking and serviceability issues like deflection and vibration control. To make things even more challenging for the engineer, accurate prediction of actual deflections and vibration is very difficult. And that may cause the engineer to use traditional design rules or other crude methods to approximate those responses. Using those approximate methods may force designers into thicker slab thicknesses, which then may result in a competitive disadvantage because competitors are designing thinner floors using other methods. Or worse, those methods can be misapplied, and that can lead to serious engineering issues and costly litigation when problems are discovered later after construction. All of those engineering risks often push engineers towards advanced analyses and design methods that typically require the use of engineering software. However, using those advanced tools and specialty applications still requires a keen understanding of complex concrete behaviors and analysis concepts. Which brings us to our goal for this presentation. Today, we will be focusing on two areas of design that may require more rigorous analysis methods when concrete floor depths are pushed to their limits: deflection control and vibration control. And a third topic that covers a high-powered optimization procedure for post-tension concrete floors. As we discuss each of these topics, we will focus on the concepts and the background behind the methods, rather than offering a simple how-to guide for implementing them in your design workflows. The goal is to better understand what the methods are doing and how they align with the design code so that you can more confidently design economical, sustainable, and high-performing concrete floors. Let's start with the first of those topics, deflection control. AS 3600 has explicit requirements for deflection control, which are covered in section 2.3.2. That section includes total vertical deflection limits and differential deflection limits after brittle finishes are installed. The methods used to determine the slab deflections are covered in clauses 9.4.2, 9.4.3, and 9.4.4. The methods include a deemed to comply method, which defines a span to depth ratio that, if met, requires no additional deflection calculation. A simplified method, which is based on an effective span to depth ratio. That method also accounts for time-dependent creep and shrinkage effects. And then finally, a refined calculation method, which is an advanced deflection calculation method like the one referred to in the introduction. This real-world slab deflection example illustrates how the predicted slab thickness required to meet a target deflection limit changes for each of the three AS 3600 methods. As expected, we can achieve the same deflection control with a thinner slab as the calculation method becomes more refined. In this case, we see slab thickness reductions of 20 to 25% using the more refined calculation method. Using the advanced calculation for this slab would save between 110 to 150 cubic meters of concrete per floor. That savings would also result in calculated embodied carbon reductions, which would be an added benefit of the refined calculation. Let's take a closer look at advanced deflection calculations then. Clause 9.4.2 in AS 3600 has a good list of allowances that must be considered in the refined deflection calculation method. This slide has a similar list of considerations, which we will focus on this part of the presentation. To accurately predict long-term deflections, we will need to consider first whether concrete sections are cracked or uncracked, and then how that affects the stiffness of the floor. Also, for concrete cracked sections, we need to account for the tension stiffening effect of the concrete between the cracks. Creep and Shrinkage strains, which are time dependent, also need to be considered. And finally, we need to consider how the applied loading and the concrete properties change over time. Let's review cracking and tension stiffening. Cracks initiate when an applied load or strain produces a tensile stress that exceeds the cracking stress. When a crack forms, stress is relieved at the crack location. It's transferred to the reinforcement, and the stress redistribution redistributes to adjacent locations. This stress redistribution may cause cracks to form in other areas. The behavior then is nonlinear and non-elastic. At crack cross-sections, there is a decrease in stiffness and an increase in cross-section curvature, which leads to increased deflections. Tension stiffening refers to the ability of concrete to resist tension between cracks and the stiffness that is provided by this tension. As shown in the image at the bottom of the slide, tension stiffening is accounted for in deflection calculations by interpolating between the calculated cracked and uncracked curvature. The equations shown in the image represent the tension stiffening model in Eurocode 2. Refined deflection calculations account for incremental creep and shrinkage strain over time, and then accumulate the effects over the loading history. In AS 3600, you will find detailed equations for both creep and shrinkage over time. It may seem obvious, but it is important to use these defined code equations when calculating creep and shrinkage strains for your designs. The image shows the shrinkage curves calculated using equations in ACI 209, Eurocode 2, and AS 3600. Note the significant differences, especially with the Eurocode 2 model. When using a software application for refined deflection calculations, then, it is important to understand which models are implemented, and if the one in your design code is not implemented, how the available models might differ from the one that is required. Restraint to shrinkage causes a buildup of tension stress, which can then lead to significant concrete cracking. We like to distinguish shrinkage restraint into two categories, external and internal. External shrinkage restraint is primarily due to stiff supports. Concrete floors that shrink tend to displace toward the center of rigidity of the floor. And then when stiff supports restrict that movement, tension stress is induced in the concrete, which then leads to cracking. Internal restraint, often referred to as shrinkage warping, is primarily due to the restraint of steel or post-tensioning reinforcement contained in the section. As concrete shrinks, the reinforcement is compressed and an equal and opposite tension force is induced in the concrete. When there is more reinforcement on either the top or bottom face of the concrete section, the unbalanced restraint causes a warping of the section. That curvature adds to the curvature associated with externally applied loads. Internal shrinkage restraint can be calculated using first principles if the reinforcement contained in the cross-section is known. External shrinkage restraint, however, is difficult to calculate because a complex, nonlinear solution would be required. Some engineers approximate this effect by reducing the modulus of rupture by a certain percentage. One disadvantage of that approach is that the external restraint becomes a function of the applied load. However, in severely restrained floors, it is possible for shrinkage restraint to cause cracks in the absence of any applied load. For that specific case, you would not want to reduce the modulus of rupture to 0 if you wanted to capture that exact behavior. Another approach to account for external shrinkage restraint is to increase the shrinkage strain by a factor based on the severity of the restraint. This method avoids the disadvantage mentioned for the other method but requires some engineering judgment regarding the level of restraint, and then also an appropriate factor to use. Load history is an important consideration for accurate deflection prediction, especially for structures subject to significant construction loads that cause early age cracking. In general, calculated final deflections at the end of the load history will be greater the earlier in the load history that cracking occurs. For deflection calculations, the goal is to capture the exact point when cracking occurs and then consider the cross-section cracked for each remaining loading stage. Consideration of how concrete strength and stiffness changes over time, especially in the early ages, is very important. Defining loading sequence as shown on the plot here also better captures creep effects because the magnitude of the applied loads and their actual duration over time are known explicitly. Finally, the loading sequence is convenient for accurately controlling differential deflection limits after brittle finishes are installed, like those limits that are defined in AS 3600. One final note when using software for calculating refined deflections. Because of those demanding project deadlines and the complexity of the calculations, it might be tempting to accept the deflection results without studying them in depth. Here are 2 tips that might help you avoid treating your software application and results like a black box. First, use stress plots to visualize where cracking is predicted. You can do this by carrying the calculated analysis stresses to the concrete cracking stress. Second, if possible, extract and study the interpolated cross-section curvatures calculated from the tension stiffening model. This will also help you determine how much stiffness of the floor is decreasing due to cracking. Both of these tips can help you gain a better understanding of the output, catch possible input errors, and identify areas of floor that might require a closer inspection. At this point, I will turn it over to Jonathan, and he will cover the other topics planned for our presentation today.
All right, thank you, Carl. I'm now going to discuss the next topic in the presentation, which is vibration control, and with an emphasis on footfall-induced vibrations. Vibration considerations have begun to make their way into building codes and standards, and as such, they've increased in importance recently. Vibrations can be induced by machinery, by vehicles, or people, and they can also affect equipment or people. So people walking on a structure can disturb other people that are on the structure, or they can disturb sensitive equipment, such as certain microscopes. While there's several simplistic methods to calculate vibration acceptability, they're often too approximate for complex irregular floors that are common in concrete construction. So the approach outlined in the design guide shown is generic and comprehensive and applies regardless of geometry and materials. So it can be used on concrete structures, steel structures, or a mixture of the two, and can accommodate any geometry. So mode shapes and their associated natural frequencies are the shapes that the structure naturally tend to vibrate. Natural frequencies and modes of vibration are characteristics of a given structure and are a function of the stiffness and mass. Floors with a lower stiffness have lower natural frequencies, which can make them more susceptible to vibrations. The more amplitude a node has at a given location, in a given mode, the more likely that mode can be excited by a dynamic load at that location. And also, if the frequency of the dynamic load matches the natural frequency of that mode, then the response can build up over time, which is a phenomenon known as resonance. So we need a way to quantify the dynamic loadings that we will use for footfall. And the loading shown with the red curve is the design footfall shape used in the design guide and was developed using measurements of actual footsteps. This shape can be decomposed into 4 simple harmonic loads, which are the dashed lines in the graph, which are integral multiples of the fundamental excitation frequency. And decomposing into simple harmonic loads allows for solution of these simpler loadings using either a closed form solution or a modal analysis. The response from a closed form solution loses its phase information, which means that we can calculate a maximum acceleration for each of those harmonic loads, but we have no knowledge about when that peak occurred. So they must be combined using an approximation such as square root of sum of the squares. A modal analysis maintains the phase information and can be combined using modal superposition and is therefore more accurate. This chart shows the results of the 2 approaches for a given problem, and they're generally close. And it also demonstrates that the results, the resonance or buildup of response when one of the first 4 harmonics matches the natural frequency of a given mode. So that's when resonance is occurring, and that's where you see the peaks in this graph. This type of resonant response is most predominant in modes with natural frequencies less than about 15 hertz. Impulsive response, on the other hand, tend to be more predominant in modes with higher frequencies. And they are characterized by an initial peak response with a rapid decay occurring before the next cycle occurs. So in this case, there is no buildup of the response. Damping is one of the parameters that is part of any closed form or modal analysis solution. The graph on the left shows the free vibration amplitude of a structure in an undamped environment if initially forced to an initial displacement and then released and allowed to vibrate freely. The graph on the right shows the same structure where damping decreases the amplitude of each cycle. So therefore, damping has the ability to counteract the resonance effect. Typical values of damping ratio in reinforced concrete structures is on the order of 3%, but it's variable and it depends on a number of factors, including the attachment of non-structural partitions, cladding, and potentially other factors. The objective of solving the vibration problem is to determine a velocity or acceleration that can be compared against a threshold value to determine acceptability. Root mean square or RMS values are used to calculate and measure vibrations, as they are better predictors of response than peak values. They can be thought of as a mean response. The curve on the left is the base ISO curve for root mean square acceleration, which is meant to represent the threshold of human perception. It is somewhat subjective, as some people are more sensitive to vibrations than others, and humans are also more sensitive while in a horizontal position, such as while they're sleeping, than in a vertical position, such as while they're standing. This curve also shows that humans are more sensitive to vibrations in the 4 to 8 hertz range. The table on the right also shows velocity thresholds for various use cases and introduces the term response factor, which is just a ratio of the baseline ISO curve value. For example, the accelerations on the baseline curve on the left correlate to a response factor of 1. There are several input parameters you might expect to input into a program when calculating response to footfall. Dynamic modulus is a measure of the vibratory stress-strain ratio and is generally higher than the static modulus. We also normally input minimum and maximum footstep frequencies, as each person has a different stride rate and rate of walking. You might be walking quickly, you might be walking slowly. So you have to evaluate a range of footstep frequencies, and each of the first 4 harmonics in that range is capable of generating a resonant effect in closely matched modal frequencies. So all of those different possibilities have to be evaluated. And resonant and impulsive response are calculated and can be considered separately. And resonant response can be calculated also using the closed form solutions, such as the one in the design guide, or also a comprehensive modal analysis. This slide shows a mildly irregular structure with the first 4 associated mode shapes from an analysis. Note that the mode shapes for even a slightly irregular structure can get somewhat complicated and are important when calculating the vibration response. So this slide shows contour plots showing the maximum root mean square acceleration and root mean square velocity response of a structure to a given set of input parameters. These values are useful if you're comparing directly to acceleration or velocity threshold limits. This next plot shows a contour plot of the response factor. And again, a response factor of 1 is the threshold of human perceptibility. And response factors can also be computed for other limits, such as operating rooms and hospitals or sensitive equipment thresholds. And response factors, therefore, are perhaps a somewhat more convenient way to evaluate vibration threshold criteria. They don't require knowledge of a particular velocity or acceleration threshold. Once you know the response factor you are targeting, you can use that factor in a contour plot to identify potential problem areas. So the last topic of the day is PT optimization. And let's start by defining what we mean when we use the term optimization. In general, it consists of finding the most optimal solution to a given problem. In the case of PT structures, we're often referring to the solution that is most economical, that is with the one with the least overall cost to construct, and that still meets all the necessary design and performance criteria. We can start by looking at a very simple example consisting of a 3-span, 2-cantilever frame with variable low point profiles in each span and variable high point profiles at the cantilever. We also have a variable number of strands in each span. One option for finding the most optimal solution is to evaluate all of the different possibilities. However, in this very simple problem, there are over 126 million permutations. You might be thinking to yourself that you can intuitively select the most optimal solution. And for this simple case, that might be possible. But in more complicated and irregular shaped structures that are commonly constructed today, that assumption is quite potentially not correct. So what is an engineer to do? One possibility is to utilize cloud computing to analyze all the possible solutions and compare them to find the most optimal one. While the use of a number of computers in parallel certainly helps, trying to analyze all the possible configurations in a complicated model could take months or even years. So obviously this alone can't solve the problem. We need a more intelligent way to narrow down which trials we calculate and which ones we can ignore. And that's where genetic algorithms come in. So genetic algorithms are an intelligent way to select which trials to calculate and which to skip. They start by describing the problem into a chromosome, which consists of real structural parameters. In this case, we're looking at the number of strands and the profile elevations. Each complete chromosome defines a trial solution that can be calculated and evaluated to see how good or bad it is. And the algorithm starts off with an initial population of chromosomes, which are generated randomly. The best chromosomes from each population are kept and then bred to create new chromosomes to evaluate in the next generation. For the evolution to work, we need a measure to evaluate our solution so that we can select the fittest chromosomes in each generation. For PT slab design, we use the total material and labor costs as a fitness measure. But we also want to weed out potential solutions with design code failures. We don't want to include those. So one way to do that is to introduce a cost penalty for code failures. So that's added into the fitness value as well. And again, when we're evaluating fitness values, lower is better. We're looking for the most economical solution. So the way that these things are bred, if we look at 2 example chromosomes on the top of the screen where chromosome 1 is green and chromosome 2 is the dark blue, one of the first mechanisms we have for breeding is called crossover, where we create splice points in the chromosomes and then swap the different sets of values between those splice points. So you can see on the crossover line, you see 4 newly generated chromosomes that have some green and some blue values in them. The next mechanism that we have at our disposal is called mutation. That's where we randomly take a particular part of a chromosome we call a gene, and we mutate that to a different value. And so that introduces another level of randomness for us and helps us make sure that our algorithm is staying on track. So again, in an optimization problem, the lowest solution is best. We want the lowest fitness, which translates to the lowest cost. And this chart is a typical convergence chart for a PT optimization. And in the early iterations on the left there, you see that it's working to find a valid solution, where the vertical distance between the purple and red curves is that the penalty for failures that we talked about in the previous slide. In later iterations, where it has found populations of better solutions, it continues to breed those to find better and better solutions. And the only real way to know that you've found the optimal one is to compare it with thousands of other intelligently selected trials, such as using a genetic algorithm. So this type of solution often results in solutions that can have 15 to 20% less total reinforcement and labor cost than an engineer might design using intuition and standard practice. And one of the biggest advantages of the optimization process is that the design is accomplished automatically as a byproduct of the optimization, because we're weeding out all of the trials that have code failures. So those don't get included as they get included in the optimization. They just have a much higher fitness value, as we can see on the red part of the curve on the left. So rather than an engineer spending hours or even days producing a design that they have little time to compare against other solutions, they can just spend a few minutes setting up the optimization parameters and ranges and let an optimizer do the rest. One possibility this creates is very rapid comparisons of different structural schemes in early stages of a project. In this chart, a comparison was done on a podium slab to evaluate the most optimal slab thickness. And a traditional approach would require tedious calculations for each of the different thicknesses, which would also be very time-consuming. So using an optimizer, the general parameters were set up, and each different thickness could be optimized in parallel with just a few seconds of additional effort. So the total cost results, represented by the dark blue line, you can clearly see where the minima is there. In this case, it's a slab thickness of 10 inches. And this conclusion is backed by thousands of real calculations on trial slabs of all representative thickness, so that the engineer can have confidence in this result. Well, Carl and I would like to thank you for allowing us to present a brief overview of these important topics related to economy and sustainability of concrete floors. And feel free to contact us via email with the contact details on the slide. Thank you.
Thank you. Thank you, JD, Jonathan, and Carl. It's now your turn to get involved. As always, to ask our speakers a question, could you do so via the chat box? And please jot down who your question is directed to. Also, I want to say a big thank you to everyone who submitted questions whilst registering. I'd also like to welcome James Vizzi, the Victorian Business Development Manager Interspan, who is joining JD in the Q&A. Starting with those questions who came in on registration, a question to you, Carl, and maybe to you, Jonathan, as well, that's coming from Peter. And Peter's watching us from Queensland. Good afternoon, Peter. Peter's asking, have the theoretical and model deflection behaviours been calibrated to real-life long-term slab deflections in real buildings? Thank you, Peter. Carl.
I'll take the first stab at that, and then I'll go ahead, John.
You go right ahead, Carl. Sorry.
I was going to say I'll take a first stab, and then I'll turn it over to Jonathan, who'll have some more thoughts on this. There are some published documentation on real structure, but they're few and far between. There is more data on actual lab results. So we have calibrated the method and RAM concept to one particular study that was led by Dr. Ian Gilbert, the University of New South Wales. In fact, Jonathan authored a ACI publication that compared those results. So Jonathan, why don't you take over and kind of discuss those results?
Sure, happy to. So There was one of the most comprehensive studies I've seen. As Carl said, there aren't too many. There isn't a whole lot of data out there to compare or calibrate against. But there was that one set of study at University of New South Wales where they studied some slabs over long-term loading and considered the creep and shrinkage effects. So they measured the creep and the shrinkage, and the method has been calibrated against those and showed quite good results. One thing that may come to mind is what defines good results in the context of deflection calculations, and that's an important question to consider, because even in that study where you had slabs that were cast constructed, and loaded in a laboratory environment, that slab had 4 identical panels, I believe, and the deflections in those 4 identical panels varied by up to, I think, about 25% or more. So in the context of what's reasonable to expect out of a deflection prediction, I don't think it's reasonable to expect much better accuracy than that if the slab itself in an experimental case isn't going to be that close. So it's important to take those sort of considerations into account when you're performing your designs.
Thank you, Carl and Jonathan. And talking global now, and I also just want to point out and let our audience know that Jonathan and Carl are actually taking this Q&A from Virginia on the east coast of the US, which is it's rapidly heading up to midnight. So a big thank you to you both, big effort. Bringing you in, James, we've had a question about how common is PT in the Australian market, and has it been adopted worldwide? James.
Thank you very much. Yeah, look, in the major cities in Australia, it is the predominant method structure or construction for mid to high-rise structures, and it is sort of growing in the small residential structures. You'll see in particularly Melbourne and Sydney, essentially all the cranes around the CBD, highly likely that is a post-tension structure. So it is the predominant method of construction. It is growing in regional areas. It's a bit limited in that it does require skilled labour, so which is the issue out in regional areas. But it is sort of growing, and we are sort of seeing it head in regional Victoria, which is where we're based, or we're based in Victoria. So regional Victoria is what we're seeing, so growth there. And we also are also seeing it grow in the other major cities in Australia, so they're not so large, but they are growing there. Worldwide as well, so we are seeing an uptake. So all of the Interspan offices are growing, which is really nice to see. So that is an office here in Melbourne, Sydney, Perth, as well as internationally. We've got offices in London, Europe, and the Middle East, and they're all seeing growth. So it is becoming the predominant method of construction. That is due to sort of the benefits you have, which the guys all went through in the seminar. So it is more environmentally friendly compared to sort of RC, conventionally reinforced structures, due to the less materials, which then have the flow-on impacts of faster construction as well as reduced costs with that. So we are seeing it grow in all areas that we operate in.
Thank you for that. And coming back to you, Carl, we've had a question that's come in from Raphael, who's in WA. Good afternoon to you, asking you, Carl, how does the software account for long-term time-dependent deflection when there is such a variability in concrete characteristics? Thank you, Raphael. Carl.
Well, that's a good question, and it really builds off of what Jonathan was just saying about those test slabs done at the University of New South Wales. So those 4 identical slabs had a variation of 25%, I think John mentioned. So there's really no getting around the variability in some of the parameters that affect deflections. Most of the deflection methods that are used, though, are built around creep and shrinkage equations that are in the design code. And those are designed to kind of average out those effects, and they're based on laboratory testing. The variation, though, it's an excellent point. I would not shy away from like a more refined calculation method because there's some variation. In fact, as you get thinner and thinner with your concrete floors, that refined deflection is going to, in general, push you closer to the actual result. So the expected margin of error is going to be smaller as you get use those more refined calculation techniques.
Thank you. Jonathan, do you have anything to add there?
Oh, I think Carl covered that nicely.
Covered it off? That's good. That's good. Bringing you in, JD, we've had a question around, does post-tensioning cause concerns when it comes to decommissioning of buildings? Your thoughts, JD?
Yes. When we're talking about sustainability, we need to think about the whole life of the building, which also account for the decommissioning at the end. Difference between a conventional slab and the post-tensioning, post-tensioning slab will have lots of compression already in the slabs, and we have safe ways of making sure we can remove those compression first, and then what is left after that is just lightly reinforced slabs, which make it easier to just decommission.
Thanks, JD. Gregory in New South Wales, Jonathan. Good afternoon, Gregory. He's asking you, Jonathan, can the vibration method discussed be used to predict vibration responses of non-concrete structures such as steel, masonry, and timber? Great question. Jonathan.
Yeah, thanks. That is a great question, because some of the simplistic methods used for vibration analysis are very limited in what they can ascertain, and the method in the design guide that was shown actually can handle various materials and also very flexible as far as geometry goes. It's all based on really the mode shapes, and that's really a function of the solution of the eigenvalue problem. So we solve for eigenvalues, which represent the frequencies, and eigenvectors, which represent the mode shapes. And the calculated responses are based upon those frequencies and mode shapes. And those can be calculated for essentially any material or geometry. So yes, it is very flexible.
Thank you for that. And just bringing you back in, James, we've talked about PT, but we've been asked the question, is there a demand for PT in residential building? Thanks, James.
Yeah, so that's a good question. Look, we are seeing more and more residential structures being converted to post-tensions, again, for similar benefits that you see. The advantages in residential aren't as the scale's not there that the mid to high rise have. So 20% saving on a residential structure won't account to the same volume of savings, but 20% is still 20%. So we are seeing more and more residential structures be converted to post tensions. Particularly if it's where you require high spans. So you see it often for sort of ground floor slabs with car parks, where you don't want columns in your car park, so you can get a nice broad open garage, essentially, in those buildings. But yeah, so they are becoming more and more there, with the cost savings there, especially with at the moment the price of materials, as I'm sure everyone here is aware, is going through the roof. Everything in construction, so every bit of efficiency builders and clients are looking to find.
Thank you for that. Over to you, Carl. We've had a question that's come in from Roverly, who's asking you, are there any other sustainability options or technologies for concrete floors that you are following?
Sure, that's another good question. Well, cement is the component that's mostly responsible for the carbon footprint of structural concrete. So one strategy that's been around for quite some time is to use waste material like fly ash or slag as a cement replacement. And then there were two that I briefly mentioned during the presentation, so I'll expand on those here. One was voided slabs. So voided slab is taking basically a plastic object, placing it in strategic areas in the floor, and then casting your concrete, and that creates a void within the concrete. And the goal there is to reduce the concrete floor weight. And if you place those in strategic areas of the floor, you're not really affecting the structural load path as well. And then I also mentioned steel fibers, so that there's been some research that we've been following here in the US, where they're combining steel fiber reinforcement with PT solutions in an effort to reduce the amount of steel reinforcing bars that might be required. And then finally, another one comes to mind. This is more of a emerging technology that I find interesting, where during cement, trying to use a carbon sequestering technique. So actually capturing carbon in an industrial process and then mineralizing it and then injecting it into the concrete. And that carbon dioxide actually has some beneficial effects for concrete strength as well. So really new, interesting, emerging technology there.
Thank you for that, Carl. James, a question that's coming from Arvind asking you, when asked to review the design drawing, can you please advise on the lead time required to do this to avoid delays in implementing the IFC? James.
Yeah, look, that's a great question and a broad one too. When drawings come through and we are looking to optimize it with a PT solution, obviously the sooner the better. So the earlier we can get on board, the sooner we can rationalize it, try to find efficiencies and the follow-on effects. A big efficiency you do get with conversions to PT that you get the reduced slabs, reduced slab thickness, as then potentially reduced columns, reduced column sizing, all the way down to reduced wings and reduced core sizes. So you do need to get in really early to get the full benefits. In the Victorian market, here often the core and the footings are already designed, already implemented. So if you come into that stage, it's already too late. You've already cut some of your savings there, or some of the environmental sustainability savings as well. So the sooner the better, essentially, for that question. There's never too much time to get a post-engineer expert in to try and rationalize the structure. So yeah, that's sooner the better.
Okay. Thank you. And while we're over there in your office, I'll just throw to you, JD. We had a question from Kwan asking, for two-way slab, the stressing of tendons, should they be carried out simultaneously or in one direction, followed by another direction? JD.
Yes, so yes, there is a particular order that the stressing need to be done. It's usually done using our strong bend. We will design using strong bend, usually in a beam with slab, it will be the beams. So we'll do the stressing in the primary direction of the beam first, and the secondary direction in the beam, and then lastly we'll do the slab tendons.
Thank you. And we're getting some great questions, and please keep them coming through. Jonathan, a question's come in. Have you considered incorporating machine learning into your genetic algorithms used for optimization? Thanks, Jonathan.
Yeah, that's a very good question. The machine learning. Let me preface my answer by saying that I'm not an expert in the field of machine learning, and so when we talk about how that might be applied to this problem, as I understand it, you really need extremely large sets of data, and you need to know whether the outcome of that data is good or bad. And this problem doesn't really apply to that. We know there's a large solution space for this problem. There's an extremely large solution space, as we saw in one of the slides that I showed. So genetic algorithm can help us intelligently decide which options to consider and calculate, and then kind of narrow down which of those solutions is going to be best by a comparison of a lot of different choices. It doesn't require us to have a huge data set. In fact, we don't need to start with any data set at all. The original data is generated randomly. There was a consideration we had early on where we could take results of genetic algorithm computations and try to feed that into a machine learning algorithm to try to train that to come up with solutions on its own. But I don't think it would be economically feasible with the computational costs from the genetic algorithms to generate enough data to make that feasible. So the answer to the question is we did consider it, but it hasn't been done for those reasons.
Thank you for that, Jonathan. We've talked quite a bit this afternoon about materials and costs, and Bernard sent through a really interesting question for you, James, asking, thanking you and JD for your presentation, but saying you mentioned the faster construction and less material use benefits. Could you please talk about the construction costs as well? If this method is cheaper or more expensive, and by how much? Pretty difficult question, James.
That is a great question. So look, you do have the material savings are there, so you've got less concrete, less steel. But just as I've mentioned, you do have higher construction labour costs. Post-tensioning is a more labour-intensive installation as opposed to conventional steel. So there's less of it to install, which is a benefit. There's more processes for each ton of steel, you could say. So for a regular conventionally reinforced slab, a ton of steel, you install it, and then you pour the concrete and you're done. There's no follow-up works to be done. While post-tensioning work, you have significantly less steel, so you won't have that ton. You might only have half a ton in the slab. That half a ton, you need to install it. You then need to stress it. You need to grout it, and you need to cut and seal it. So there are additional labour tasks in there, which you add to costs. On a flip side, though, once you do those things, once you stress it and grout it, your slab's almost done. There's pretty much nothing else you really need to do to that slab, and it does get up to strength significantly faster. So a normal conventional reinforced slab, you're looking at about 28 days to get to full design strength, whereas a post-tension slab, you can get to that full design strength within a week, if you play your cards all right there. So you do get sort of the speed and the time as well. A good way to see, I guess, overall in the entire life cycle, which way is cheaper, or more economical, which is what the question's asking, is to again look at the buildings being built in the major cities here in Australia, where labour is quite expensive, and it is still the predominant construction method for those high-rise buildings. So based on that, experience shows that it is a more economical solution.
Thank you for that, James. And JD, a question's come in from Kim asking, are there any special requirements for PT in coastal and splash zone, like the wharf and ramp? JD.
Yes, all this is dictated by the code. We have a specific area of the code which tell us what we need to achieve in terms of concrete thickness or covers that we need to provide for these coastal areas. So anywhere you're building something in region A or region B, you will need to check with the code what is the classification of that region, and based on that, you will need to provide the cover required to ensure that your design will meet the code.
Thank you for that. And before we come back to our Bentley speakers, I just want to ask you, James, Nelson sent an interesting question through asking you, with thinner structural members, would it increase the risk of collapse under fire? Very topical.
Look, this is, I guess, similar to what JD was saying there as well, that you have requirements that need to be met. So the building will have a structural brief. In the structural brief, you'll have in it the required fire rating that the building needs to achieve. Now, regardless of how that building is built, if it's conventional reinforced concrete, if it's post-tensioning, if it's timber, if it's a steel frame structure, regardless of how it's built, a tenancy type needs to meet a certain fire rating. So whatever that fire rating is for that tenancy type, so whether it's a car park, residential, shopping centre, tenancy type, they'll have a required fire rating, whether it be 60-minute, 90-minute, 120-minute. Any construction type needs to meet that fire rating. So while you do have thinner slabs with post-tensioning, you'll still need to meet the same fire rating and the same requirements as a conventionally reinforced slab. Same as a timber building. While you might think timber burns easier than concrete, it still needs to have the same fire rating as all the rest. So they all need to come down to the same firing fallout tendency.
Thank you for that. Jonathan, bringing you back in, Armin in Sydney, good afternoon to you, has asked you two questions around the GA. The first one being, has this GA toolbox been already implemented automatically in design process in RAM concept? And the second question Armin is asking, what GA benefits leads to be selected over other optimization tools like dynamic programming and Colony and so on? Hopefully that's not too long of a question, Jonathan.
No, I think those are very good questions. Thank you for the questions. And the answer is yes, we have implemented GA in RAM concept, and that is available now. The way it works essentially is you provide an initial PT layout and provide the ranges that you want to explore. So essentially you're defining the solution space. And then you basically click the button and allow it to optimize, and it does so using the cloud. So it uses a lot of processors in parallel, and it shows you a convergence chart similar to what I showed in one of those slides. So you're able to see the progress and then also explore. You can look at any of the different solutions that it's come up with along the way. As far as the benefits of GA over other optimization algorithms, I appreciate you raising the question. There are many different optimization algorithms. And honestly, we have a lot of GA experts we have a lot of optimization experts within Bentley, and I relied on their expertise to guide me towards which algorithm to choose. And that was really the first one we started with, and discovered that it worked quite well. And so we've stuck with it, primarily just because, if it isn't broke, don't fix it. There may be other algorithms out there that would work for this problem. We haven't really spent the time to explore that in detail at this point in time.
Thank you, Jonathan. And this afternoon we've talked about the economy and sustainability, sustainability-driven designs for concrete floors. I just want to ask each of you, or maybe either JD or James, you can do that collectively, but starting with you, Carl, you talked about emerging trends, but what do you think are the biggest changes that we're going to see in this area over the next few years? Carl?
Well, one that comes to mind is, I think, and we've started to see this, is the embodied carbon calculation is likely going to come, and more engineers are going to be required to do that. And that calculation can be complex. There's a lot of variability in that equation. So I can see, at least initially, it's going to be a challenge for structural engineers to start doing that. And I look for more and more tools to come on the market to help us do that and produce more sustainable designs.
Thank you. James, JD, do you want to, from your part of the world, what do you think is the biggest changes and shifts we're going to see?
Yeah, look, I think what we're going to see here in Australia, and to be honest, worldwide, is more locally sourced material with all the supply chain issues and what we're getting. I do believe that people are going to start looking to try and firm up supply chains more locally, which, for a country like Australia, can be a really good thing, a real positive, because we do have a lot of these materials in house. I think that's going to be sort of a push to that.
Okay, thank you. And just coming back to you, Jonathan, on behalf of Engineers Australia, what advice would you have to our young engineers that are entering into this field?
Oh wow! What advice would we give young? I think the biggest piece of advice is don't use software like a black box. That really was never the intent. I think I see too much of that in the world today, where a little too much trust is put into that without understanding what's the mechanics going on behind it. So It's not a replacement for education. It's not a replacement for good judgment. Utilize those skills that you've learned at university, and continue learning and understanding what it is that the software is doing for you. Software is a tool, but it's not intelligent enough to always give you a good answer. You have to provide good input and be able to interpret results. And so rely upon your education and continue learning.
Thanks, Jonathan. Carl, do you want to add to that?
Jonathan made the point that I was going to do is definitely don't use your software as a black box. And also Jonathan mentioned to continue learning. And I gave 2 examples during my presentation with ways to avoid that. So if you're doing a deflection calculation, look for areas where cracking is predicted, vet that and make sure it matches what your expectations are. And then, with education, don't stop with what you learn in school. I would continue learning as you're working. So for deflections, delve into the articles that, say, Dr. Ian Gilbert has wrote. He has a good textbook on long-term deflections. Pick that up and study it and keep learning.
Right. And JD, advice to people coming up through the ranks.
Look, Jonathan and Carl has made very good points. We use Bentley RAM concept here as well. When I started here, I didn't know how to use the software. But what helped me is knowing the basics. You start using the software, so you get it wrong, and then you go into the software, why is this giving you something wrong? And then you use your knowledge to find out what's wrong and how to make it better, or how to resolve these issues. But don't trust blindly the software. Sometimes you will see stuff that come up and say, asking you to do something, putting certain amount of reinforcement at a certain spot, where your mind and your experience will know that this is not right. Then it's up to you to apply yourself, dig into it, and always try to find out what's wrong. And also, one thing that has helped me at the industry is always ask people that is more experienced than me. There's no shame in asking questions. And here at this span, when I started, James was a senior engineer here. I've gone to him a lot of time with questions and you learn, and that's how you become a better engineer.
Yeah, I'll just add to that. Yeah, and look, engineering is a collaboration. So it's not, you're not just by yourself. So it's collaboration. There are smart people there, and everyone should be sharing knowledge, sharing understanding. I like to see no question's a dumb question. I don't like questions being shot down either. Everyone's learning. Everyone's starting from somewhere. So everyone work together. It's always nice.
Thank you. And we are, as always, running out of time, and we have covered a lot this afternoon. And Jonathan, I just thought maybe you could help close this afternoon's session, and just sort of from what we've talked about today, if you could summarise, what are the key messages that you'd like to leave our audience with this afternoon? Thank you, Jonathan.
Yeah, thanks for allowing us to do this. There's a lot of material that we covered today. I think the idea is that we're trying to get across here that there are a lot of good tools out there to get to accomplish what needs to be accomplished in the modern design world, which is this push for sustainability, push for more economical structures, and explore the tools if you haven't used them. Learn more about them. Feel free to reach out to us to ask questions if you have any questions. We had our email on an earlier slide, so feel free to email us and reach out to us, and we're happy to help. But there are some great tools out there, and please utilize them.
Right. Carl, do you have anything to add in summary?
I think Jonathan summed that up perfectly, so I don't have too much to add right there. Thanks.
Thank you. JD, James, anything to summarise before we go?
Yeah, look, sustainability and economics go hand in hand in engineering. So looking for sustainability is also helping economics of structures. So they work together. And I guess fundamental changes like shift from RC concrete to post-tension concrete, while it may not get you green star points, if you're taking out tonnage of steel and tonnage of concrete, you are making a more sustainable structure. So even if the green star points aren't there, I still recommend look into it.
Thank you. Okay. And thank you very much to all our speakers today. And I say particularly to Jonathan and Carl, who are now in the early hours over in Virginia in the US. It is all we have time for today. Please join me in thanking JD Camden, Carl Gullaroot and Jonathan Hirsch and James for their time today. I'd also like to thank Engineers Australia's industry partner, long-standing partner, Bentley Systems, for their support. As always, we're looking for feedback from you, what we can do better, how we can improve. So if you could just take a minute and please complete a short feedback form, which is linked in the description box below. Once again, thank you again for joining us, and we look forward to seeing you at a future Thought Leaders event. Thank you and good afternoon.